My name is John Lydell, Chief Scientist at Tactical Computing Laboratories. You might remember me from such films as that guy that did that thing that one time and how to set your FPGA on fire with software. So this is actually a talk that was crafted by myself, my colleagues at Berkeley Lab, and my colleagues at MIT Lincoln Lab, Kurt Cavill. And what we're going to talk about here is actually an interesting extension that we call xBGAS. And I apologize actually for the title, because what we're not building is actually an RV128 system. What we're actually doing is trying to provide an interesting extension and ecosystem for doing what we call data center scale addressing. So xBGAS, it was sort of a coincidence that in Kirsty's talk this morning that we followed his nomenclature for building sort of extended naming extensions for RISC-V, stands for the Extended Base Global Address Space. And what we're effectively trying to do is build an extension that allows you to support RV64 or potentially RV32 binaries that are ABI compatible with your system, but give you the ability to do extended addressing to sort of talk with larger scale devices, storage, potentially large scale data centers with microarchitecture extensions. And it turns out that to do this in a very interesting and compact manner in a microarchitecture is rather difficult, because you have all sorts of problems to deal with, like memory translation, ABIs, binary compatibility layers and whatnot, that we'll get into a little bit here in a minute. And what this is actually not, for those who haven't followed this progression for quite some time, this is not a replacement for RV128. We would like you to provide you the potential mechanism and path to implement an RV128 extension, but this inherently is actually not RV128. So in terms of application domains, there's a number of things that we want to address with our extension. Number one, we have what we call the HPA flat, which is the high performance analytics flat addressing model. So those of you who are dealing with real tangible large graphs, so not graphs with millions of edges or single billions of edges, but hundreds of billions and trillions of edges, have this real interesting problem of graph sharding. And sharding a graph across multiple memory spaces tends to be very difficult. So what if you were to have a global object-based address space to allow you to map very large graphs onto a data center? We have the potential to map things such as large-scale I/O subsystems. So you can think of having multiple extended addressing domains that map to different tiers of your storage, whether it be SSDs, spinning disk, or tape. You could potentially have something like the Cloud BSP model, where you have an in-memory compute model such as Spark, and you want to actually make that accessible via your microarchitecture instead of going through all these JIT layers and all these translation layers and all these runtime layers. And what we're actually interested in is the high-performance computing aspects as it relates to partition global address space languages. So those of you who are familiar or live out here in the Bay Area, you've probably seen pictures of this wonderful system that they have out at Berkeley Lab called Cori. It's a Cray XC30 system that's very large, very scalable, and has this very interesting interconnect that allows us to do fairly low latency puts and gets across multiple memory spaces. But the unfortunate thing of doing this is there's a tremendous amount of library overhead to doing this. Even though the Aries interconnect has native support for it, the actual core processing doesn't have microarchitectural support for this. And so in order to do so, we have to go through all these software hoops and thousands of cycles in order to get these messages out on the wire. So what if we had a microarchitectural extension that natively mapped into the interconnect's address space to allow us to do these gets and puts at scale? So in order to do this, we have a lot of really interesting library examples that we can use for prototyping this. The one we're actually going to use first is Berkeley's GasNet layer. PNL has global arrays in RMCI. Cray Chapel actually has native support through UGenie for the Cray Aries interconnect, which is about as low as latency as you can get. Then there's more open models, such as the OpenSHMEM model, which is also rather interesting. So the way our addressing actually works is we use the standard RVX, X being 32 or 64-bit, addressing model, and we extended with a set of mapped registers. So you can think of having X0 through X31 with its equivalent E0 through E31 that holds an extended addressing model for your extended address space. We actually take your standard CSR bits, such as XLAN, and encode those as the base ABI model. So all of your normal applications, such as Linux's LS, your compiler stack, all of the standard tools will actually boot and execute just like they normally would. It's only when you use these extended addressing instructions do you get access to the extended effective address space. And the way we do these addressing models, you actually don't necessarily squash the addresses together to make a full flat 128-bit address. We actually use them in conjunction with one another such that you can encode things like object IDs into the most significant 64 bits. So as an ISA extension, we actually provide a set of relatively rudimentary instructions to do this that are split into three major classes. You have what we call your base integer loads and stores, and what those actually do is they mirror the set of RV64 loads and stores, and instead of just considering the base RS1 and RD registers, what they actually do is they use the base RD plus the equivalent index into your extended register file to form your extended object-based address. And that allows you to encode these in a very compact manner that looks very similar to your traditional addressing model. We also have what are called the raw integer loads and stores, and these are R-type instructions that allow you to do very, very explicit addressing. So, for example, if I want to take an individual byte or an individual 64-bit word and scatter that across multiple objects, I can actually just simply modify the object ID and use the same instruction to scatter across multiple different object targets. Conversely, I can actually stride across a single object by just modifying the least significant 64 bits and effectively do full data and DMA copies between devices. Then we have things like address management, and that allows you to explicitly read and write those extended registers for simple cleanup and management. So this is the entire ISA encoding for all of the xBGAS. So it supports all the standard loads and stores in RV64 in both the base set and the raw integer set. We have 3 address management instructions and a couple sample assembly mnemonics. Notice that there's no current support for floating point, but that's relatively easy to add. And there's no support for things like atomics, which would actually, in this case, be relatively useful in a global address space system. And that is actually one question that we would like to pose to the community is, how do we build extensions to extensions? So this is where things get a little bit tricky. Now we have to consider things such as the ABI. Well, we have the base RV32 or RV64 with the context save restore space, the call return, register utilization, all of this interesting space that we save around. Now we have to support this with these extended addresses to hope, and the hope being to support and not ruin the base ABI. One of the other set of interesting questions we have actually has to do with the linker. We've begun to prototype this a little bit with the LLVM linker subsystem that Alex Bradbury discussed earlier, and that is, how do we build an infrastructure with software where we link objects that have extended addressing capability with objects that do not? So if you have a math solver that only considers local memory space, how do you link that with a larger application that has global loads and stores? Then there's this painful topic of debugging. And how do you debug a machine with a multi-exabyte memory system? And that's an interesting grad student topic that maybe one of Kirsty's grad students can go after. So in terms of research and progress, one of the partners in the project, Texas Tech University, which I'm actually an adjunct research professor, is handling most of the software effort. Right now, we actually have a compiler based upon LLVM and the 1.9 supervisor specification up and running. They're currently bringing up the Spike simulator. And at Texas Tech, they have this really interesting center associated with the data-intensive computing lab called the Cloud and Autonomic Computing Center. And what they do is they actually do cloud infrastructure testing. So what they hope to do is actually deploy Spike out into their cloud infrastructure and do all sorts of testing, both at the application level with their cloud applications and at the infrastructure level to do sort of power and data infrastructure modifications and testing to all their instruments there. The hardware effort is led out of TCL, LBNL, and MIT. We're currently exploring 2 different potential implementations based upon pipeline and accelerators, and there's a number of other topics that we hope to address here pretty soon. In terms of community support, this is where I ask for interesting comments, interesting help. We have released the first revision of the specification on GitHub, so pull requests are absolutely welcome. Comments are absolutely welcome, and we hope to expand the spec to support some other potential application domains. The RISC-V tools branch is also on GitHub, so I suggest if you're interested in playing around with that, by all means, grab it and hack on it and see what we broke and see what we didn't break. And beyond that, just a couple acknowledgements. My colleagues at Berkeley Lab, Kurt Kevel from MIT, who couldn't make it today, my colleagues at Texas Tech, Jiwang, Frank, and Yang Chen. Bruce Jacob was instrumental in providing some interesting comments for the memory model, and the infamous or famous Steve Wallach at Micron. With that, I'd like to thank you.